Hey, physics nerds, how's it going? So we are going to talk about radiation. So this whole week we'll be doing, let me just look at my little chart that we got going on here. Isotopes, forces nature, binding, energy, mass defects, and radioactive decays, alpha and beta and gamma. So that's all this radiation stuff. So back in the day, in 1896 here, it was discovered by Henry Becquerel that some elements were radioactive. And then from there, a whole stem of type of physics came from that. Madame Curie started working with it, and she got her Nobel Prizes and stuff like that. So they emitted some sort of radiation. It was all discovered by accident, right? So you had this chunk of radioactive ore. He put it on top of a photographic plate. He put something in between it as well. He put it on his desk, and it went through his desk, and it exposed the plate. And he was trying to figure out, how did that work? How did this ore expose the plate? Photographic plates are just special types of material that are sensitive to EMR radiation, such as gamma radiation. So he's trying to figure out how that worked. Also, around 1911, so Rutherford, when he was doing his gold foil experiment, he also determined the size of the nucleus in relation to its atomic number. It gets this little formula here, but not too concerned about that. But this led to the discovery on the next page here that in about 1918, Rutherford discovered that protons were some kind of fundamental particle that when he was transmuting nitrogen into oxygen, and you could do that. And they did that back in the day too, by just shooting things at each other at high speeds. So you pull up my periodic table here. I got nitrogen, you got oxygen, right? So he found that nitrogen transmutes into oxygen, and the process produced, well, actually probably go the other way around. Oxygen transmutes into nitrogen, whatever it does. It kept on producing these helium or hydrogen atoms, these hydrogen nucleus, I should say, not atoms. Because remember, an atom has electrons, a nucleus does not have electrons. It's a charged particle. So he concluded that these hydrogen nucleuses were a fundamental particle. They were constituents of all nuclei, and he called them protons. So a hydrogen nucleus, a hydrogen 1 nucleus, is just a proton. Okay? He also discovered that these protons didn't account for all the mass inside the nucleus. So his partner Chadwick, I said Chapman before, but it's Chadwick. It's one of the videos. They hypothesized that there's this neutral piece approximately the same size, mass of the proton. It says here it's about the same. We'll talk about it later on. They are slightly different from each other. A proton and neutron are not necessarily the same size, but they accounted for the other mass that the protons didn't account for when it came to the atomic number. And the atomic number, and what we know about the atomic number, is it's just the number of protons in that element. So if I have an atomic number of, say, 47, atomic number of 47 is silver, right? That means it has 47 protons. If it gained a proton, it become cadmium. It have a different property. So the protons pretty much tell you what the property of the atom is. So like if I have gold and I add a proton to it, I get mercury. Mercury is a totally different element. It has liquid properties at room temperature. So you change its characteristics by just changing its protons. Not changing its neutrons, not changing its electrons, but changing the protons. Okay? So we're going to deal with what we call nuclear notation here. So on the top of a nuclear notation, so if I'm going to write out an atomic number or element, so this is element X doesn't exist. Just a random thing. This could be He for helium, could be Ag for silver, Au for gold, Ca for calcium, etc. Okay. Oh, sorry. The bottom number, the atomic number, Z here, is going to match the atomic symbol, the chemical symbol, right? They're not going to change. So if this is calcium, this bottom number will always be 20, right? If this is helium, the bottom number will always be 2. If this is silicon, the bottom number will always be 14. So those always match each other. Now the top number can change. Right? It doesn't always have to be a nice constant number. With fluorine 19, the top number will be 19. Like a fluorine 20, so the top number will be 20. And what that tells us, it tells us the number of nucleons. There's a nice little key word there. Nucleons that are inside the element. Okay. Now, nucleons are just another fancy name for anything that's inside the nucleus. So that would be the larger pieces, the hadrons, I should say, that are inside the nucleus, the protons and the neutrons. So if I ever say, how many nucleons do we have? I want to know it's protons plus neutrons, the sum of those two things. So the bottom number is just protons, and the top number is neutrons and protons together. Okay? So that should be pretty easy. So if say I have gold 197. Now, the numbers that you see on the periodic table, so gold here is 196.97. What that number is, it's the average of all the different isotopes that you can find out there. So 197 is the most common isotope, so that's why it's 196.97, so it just rounds to 197. That's the most common, right? So these top numbers are always whole numbers. So this 197, that's a whole number. They're never these decimal numbers that are on here. The decimal numbers is the average of all these isotopes. This is one very particular isotope, 197. There's gold 200, there's gold 202, there's gold 196, there's gold 195, right? So there's a bunch of different types of isotopes of gold. This is just one particular one, but if I just grab a bunch of gold in my hand, most likely I have a bunch of different isotopes in there. So this one is called gold. Usually when you write it out, you could write out gold 197. It's a very specific type, right? It has 79 protons, right? Its atomic number is 79. That's why it has that many protons. Yep. And the number of neutrons, so this number, the 197 is the protons plus the neutrons. There's a little equal signs here, because we could just use math or just a little bit of algebra to solve these for us. So I'm just going to subtract these around, so we know this is 79. So if I want to find the neutrons, let's just subtract that 79 over to the other side. Let's see, 197. It's too late in the day to do mental math here. So I got 118 neutrons. Okay? Yeah, so I was saying, like, I could have gold 200, which I have a different number of neutrons. It would be a more massive molecule, but have the same properties of gold, because the properties of gold are dependent on the protons. Because the protons change the energy shells, how many electrons you can actually have, and how many shells or the orientation of those clouds that you saw in the Bohr model. So that determines the property of that atom itself. Find the atomic mass number of uranium that contains 92 protons. You can look around here, let's see if that's true. Yeah, uranium's 92. And it has 146 neutrons. So its atomic mass number is going to be, hope I'm using the right numbers. Its atomic number is that, the atomic mass number, yeah, is going to be the number on the bottom. Now I can go here and find uranium's number. Uranium's number is 238.03, so that's the average. But the atomic mass of this one, the atomic mass number of this one, is just going to be the addition of these two numbers. So 238. Oh, it's actually really close. Use the average number there, so they just rounded it down. But it's an exact number. Atomic mass number is 238. So this is uranium 238. So I'm just going to write that down. Nice whole numbers there. So we never use decimals in the nuclear notation, and we never use decimals in the nuclear notation written out that way too. Okay, so many of, like I was saying before, many isotopes or elements have isotopes. So long as they have the same number of protons, they're considered the same element, but they could have differing neutrons. So this isotope, right, has 57 nucleons in it, 30 protons. I'm just going to go here and just find out what it is. So I look up 30 on my periodic table. 30 on my periodic table is zinc. So this is zinc. And this isotope is zinc 57. The most common zinc is 65, right? If I round that number, if I round that number down, it would be 65. That's the most common isotope. So zinc 57. So most likely this is probably radioactive as well. Usually the non-common ones are radioactive. We'll talk about that later on. So here we got 80. So I look at my periodic table and try to find 80. Okay, that's mercury. Mercury. And this is mercury 187. Is that a heavier or lighter version of this? It's a much lighter version of mercury. Mercury is usually at least 200 or 201. This last one here is nitrogen. It's nitrogen 13. Nitrogen is usually 14. Cool. There we go. So we're just looking at the bottom numbers. This is the proton count. And then you just look up that proton count and then find out which element it is. So here's a bunch of nuclear notations of these isotopes. So you have thorium-227. So thorium-227. So I got 227 on the top. I had to first of all find out what thorium's chemical number is. Now, usually to find these out, rather than just kind of searching everywhere, you look at this top number, this 227. You look at elements around that. So look for 227 on the periodic table. Not proton numbers, but the mass numbers. 227 is TH. So it is thorium and has 90 protons. All right, so I just looked that up. Fluorine, 19. You look at fluorine, you should know where that is. That's a 9 there. And there we go. And radium, there's a couple of things that, there's like radon, radium. There's a few things that look similar, but radium is Ra. It's 223. There's usually 226. And it is atomic number of 88. There we go. Okay, so usually when we're talking about this, we're going to do some more math. This is pretty easy stuff. This is the stuff you should know from chemistry, science 10, chemistry 20, 30, etc. But usually for calculations, when we're talking about this, we want to talk about its mass as precisely as possible. Right? So when we deal with these, there's such small numbers. Like if I look down at my chart down here, we got the masses of an electron, the mass of a proton, the mass of a neutron. You notice they are slightly different from each other, but they're also really small. So we define a new type of unit to measure mass. We call this the atomic mass unit. And it's defined by taking carbon-12 atom and dividing it by 12. Whatever the mass of a carbon-12 atom and divided by 12. And carbon-12 is used in a lot of places, like a mole is defined by a gram of carbon-12. There's a bunch of other things too. How many particles in a gram of carbon-12? So it's a pretty well-established number, this carbon-12 mass, which is divided by 12 because there's 12 things in there. And each piece, because each piece actually weighs a little bit differently because there's 6 protons and 6 neutrons in there. But they weigh slightly different, but the average of each of those pieces is 1.66 times 10 to the negative 27. You look on your periodic table, you'll find that, or not a periodic table, but the formula sheet. If I had a formula sheet on me that had this constants on it. Weird. Oh, nope, I lost it. Doesn't matter. Okay, but it's 1.66. All these little sig digs on the bottom afterwards. Therefore, more precise calculations. I might use those in some calculations, but most of the time I'll just use 1.66 times 10 to the negative 27. So by using these atomic mass units, I can convert these numbers, these masses, by just taking these and dividing them by the 1.66 times 10 to the negative 27 kilograms per atomic mass unit. And they use a lowercase u for those. So I'm just going to divide by this 1.66 to get to those numbers. So you can see that these numbers, they're slightly more than that, which is, it's kind of weird. We're going to talk about that a little bit later on. That protons and neutrons weigh more than, so 12 protons and, so we got to come back. 6 protons and 6 neutrons would weigh more than 6 protons and 6 neutrons inside carbon 12. Because that's what's in here. So up here, this is 6 protons, 6 neutrons. So the mass of these are different than if I just multiply these by 6 down here. That's weird. That is strange. We'll come back to that. Okay, so the masses are not quite the same, because if these were the same, these should be just 1, 1, 1, rather than be 1.007 and 1.008. These would just be 1. Then they would match. This would end up being 12 atomic mass units. That would be 12 atomic mass units, but they're not quite the same. They weigh more when they're not inside the atom. Okay, we'll come back to that. Before we go any further, can gravity hold 2 protons together? Because protons are the 2 positively charged particles, so they're going to be really, really, really close to each other. So 2 positives should repel each other. So I'm going to finish off this here, and then we're going to talk about the binding of what holds these things actually together in the next videos. Let me talk. Oh, actually, maybe not. Yeah, I'll stop in this first sentence here. Okay, so let's first of all, let's figure out if gravity can hold these 2 things together. So you have 2 protons. Gravity is going to pull them together. So Fg is going to hold them together. And Fe, the electrostatic force between them, is going to try to repel them. So I want to know, is gravity more than Fe? All right. And if it is, then at least they're going to hold together. Because it would make sense that they would hold together because they're inside the atom, really, really close. They are 5 femtometers away from each other. Right? And nucleuses are really, really small. Lots of protons in there. Lots of things holding or trying to push each other apart. So something's holding them together. So it makes sense it'd be gravity. So let's double check. So to find the gravitational force between 2 people or 2 objects, so I would take G times M divided by R squared. So G is 6.67 times 10 to the negative 11. I believe that's the G number. The mass of a proton, let's go up here, the mass of a proton. So just go 1.67 just to simplify our numbers a little bit. There's 2 of them, so I'm just going to square it because it'll be the same number times itself. And I'm going to divide by, I'm going to lose my whole work there. Okay, I'm going to divide by the radius, which is 5 femtometers. So that's 5 times 10 to the negative 15 meters squared. Cool. Okay, let's plug this in my calculator here. Square that. And I'm going to divide by the femtometer number squared as well. So we get a force of gravity of 7.44 times 10 to the negative 36 newtons. Okay, it's pretty small, but maybe because it has a really small charges, the Fe, which is calculated by going KQQ over R squared. So it's going to look very similar, but we're going to use 8.99 this time, times 10 to the 9. We're going to use the 1.6 times 10 to the negative 19 coulombs. Same number because it's 2 protons. That number is, again, that's on the periodic table, not periodic table, but the constant side of your formula sheet. You'll see proton, beside it you see 1e, and an e is an elementary charge that Millikan found. Okay, and let's put the femto number in there. Let's punch this in my calculator. 8.99 e to the 9 times 1.6 e to the negative 19 squared. Let's divide that by 15 squared. 9.21 newtons. They're considerably different. One is considerably larger than the other. It is Fe, the repulsive force, is 1.23 times 10, or sorry, it says 3 times 10 to the 36 times larger than Fg. So is gravity actually holding these together? According to this, they're not, because gravity is so much weaker. Gravity is the weakest of all the forces. So gravity cannot hold two or more, because there's going to be more protons in there, all pushing each other, protons together. In the nucleus. Can't, right? You can't do it. So something else must be holding them there, right? And this brings us to another fundamental force. So far what we have is gravity. We have electrostatics, or electric forces, magnetic forces, which we'll put together. We call them an electromagnetic force. So technically we have two forces there. So gravity and electromagnetic force. And then we have this new force that we have to introduce here that's going to have to hold these together. And this force is so strong that it has to overcome that Fe. The problem is, if there was a force that was so strong that it has to overcome Fe, then wouldn't that overcome Fe everywhere and everything would just kind of clump together all the time? Well, they kind of show that through experimental forces, that once you're past that femtometer distance, apart, like about 15 or so femtometers, once you're outside the atom, this new force just kind of disappears, right? If you're a little bit more than a few femtometers apart, it just disappears. It drops off significantly and it's gone, right? So there is a limitation to this new force, and we call it the strong nuclear force because it's within the nucleus. It binds protons and neutrons together, right? It's negligible when you're far apart, but it's huge when you're together. And that huge force is holding it together. Now, where does that force come from? Where's this new force coming from, right? And we'll talk about in the next video, in the next lesson, actually. And I'll see you then. Bye.